All right. Good afternoon, everyone. I am Pavlos Protopappas. For the few of you who don't know me, I'm the scientific director for the Institute for Applied Computational Science. This is our seminar series. This is our first speaker today for the fall. We have five more speakers lined up. Next one will be Ben Brown for University of Colorado in sometimes mid-March. What's the question? No. And then we have a few more talks. You can find all this information on our website. IACS seminars, you'll find the information. So today is my great pleasure to have Matthew. Matthew and I go a long time ago. We were collaborating for many years. It was easy to even write his bio for research interest because we were very close to each other, so I can just repeat my research interest, and that will do it. But Matthew is a research professor at CalTech. He is the project scientist for ZTF, which ZTF is a big survey happening as we speak, the last 9 months to a year, collecting terabytes of data and interesting physics astronomy coming out of that. He will tell us a little bit about that. Yeah. Also, ZTF is the predecessor for the LSST, which is going to be coming in a few years. If you have any interest in astronomy, that's the next big thing coming up. He has his PhD in astrophysics from University of Central Lancashire. Then he did a postdoc at Imperial, followed by a postdoc at CalTech, became a research scientist there, and eventually he ended up becoming a research professor at CalTech. Today he will be talking about some interesting talk about predicting aperiodic behavior for astrophysical time series of light curves. Please help me to welcome Matthew here. Thank you, Pablo.
So thank you very much for inviting me. I've had a very pleasant couple of days here already in Boston, meeting Pavlos and people in his group and various people at CFA as well. So I'm going to talk broadly about some work that I'm sort of doing in sky surveys, and particularly with quasars and sorts of questions of modern approaches that we're trying to use to understand the physics underlying quasars, but it's more broadly applicable to sort of aperiodic astrophysical behavior, and so that's what I'll cover. So I have this thing called predictive modeling, and this is a phrase I came up with for an NSF proposal, and I like it. But we've actually been doing this sort of thing for a very long time. And we like to do predictive modeling because for 2,000 years, when we saw anything in the sky, we would make a note of it and think that, oh, it's a terrible thing, you know, the world's going to end, Constantinople's going to fall, you're going to have two-headed babies born and fire and whatnot. We're a little less, most of us are a little more sensible in sky surveys these days, but a lot of the sky surveys, and ZTF is not separate from that. A lot of us, there is a component about near-Earth asteroids and killer asteroids and all this sort of thing. So we are obviously still looking at the sky, looking for the things that are going to plow into us, if not necessarily blow up. But the sorts of things I'm going to be talking about are a little further out and probably less relevant for us. But we're in this era of the last 10, 15 years or so, a real explosion of time domain astronomy. And some of this is coupled by detector advances where we can build bigger and bigger cameras, and so we can get bigger fields of view. We have more robotic telescopes around the world now, so there are systems where you don't need to go and be the night observer who's doing the photographic plates or whatever. You can just set up the robotic system, it'll move, it'll do everything, the data flows, it goes through a pipeline type approach. From, you know, sub-meter class things up to 4, 5, 6 meter class telescopes. And then, of course, there's this build-up, or there's this new set of space-based missions as well, things like Gaia, where they're looking at the same area over and over again, ostensibly for some types of science, but it builds up a data set where you have many repeat observations of the same area of sky and allows you to start saying, well, it's not just as though I've got, I can go across the road and look at the Harvard plate catalog and see something from 1900 and see how it looked 25, 30, 50 years later. Now I can see what did this look like 3 nights ago or a week ago or a month ago or a year ago and get a much better idea of what the dynamic timescales and things are. And of course we have not just optical, we have this right across the electromagnetic spectrum, and then we have things like LIGO and IceCube, which are taking us into regimes of physics where we never thought we would be able to have any detectability or anything like that. And it's all time domain driven. It's all this idea, I detect something here and then I want to follow up and see what the optical counterpart or whatever it is. So I've been involved in 2 big surveys leading to this. One is the Catalina Real-Time Transient Survey. So this is, CRTS is a piggyback survey. This is run out of CalTech for the last, 2019 now, last 12 years or so. But it actually sits on top of the Catalina Sky Survey, which is a near-Earth asteroid survey that's run at the University of Arizona, the Lunar and Planetary Lab. They're interested in anything in the solar system. They don't care about anything outside of the solar system. So if it's outside of the solar system, we get it. If it's inside of the solar system, they get it. So we piggyback on top of them. So it's 2 telescopes in the northern hemisphere, and then there was one in the south. It's a 0.7 meter and a 1.5 meter in Arizona, and they're just looking for asteroids going to plow in. But what it is, it covers the northern sky maybe once every 10 to 20 nights to 20th magnitude. But because it's been going on for 10 or 15 years, it's a wonderful data set for the northern sky. There's smaller coverage for the southern sky, but there's about 8 years worth for the southern sky. And so you get for any astronomical object between about 12th and 20th magnitude, maybe sort of 300 observations over a 10-year baseline in a single filter down to about 20th magnitude. So in terms of temporal coverage, it's just like LSST. In terms of data volume, it's about a 2% LSST. So I've done a lot of work on this and systematic exploration of behaviors of particular types of objects or particular classes of objects in this data set. It's all available online. And I'm now, as Pavlos said, the project scientist for the successor, in some ways, to this, which is the Zwicky Transient Facility. And you may have seen our first batch of papers and press release, which came out last week on archive and such. So this is Palomar Observatory. We use the 48-inch telescope. So this is a camera on the 48-inch. It has a 47 square degree field of view. So it's exactly the same as the old POS photographic plates. So this is the first survey which is actually reproducing what Zwicky envisaged back in the 40s and the 50s when he built this. Various details, and I'll cover those a little bit more. One of the things that we have at Palomar, one of the nice things about private institutes like Harvard and CalTech is that we're well resourced in terms of telescopes. And so we detect things with the 48-inch and the camera, and then we have follow-up facilities with the 60-inch. We have a small integrated field unit spectrograph on there, and then we have the 200-inch for doing deeper spectral observation, and we can go to Keck if we need to in Hawaii for even deeper. So we have a whole sort of discovery engine system here, but a lot of what we're doing is public as well. In terms of, as I was saying, CRTS is a sort of 2% LSST. You can think of ZTF as a 10% LSST. So LSST comes online in 2022 nominally, so we're very much a stepping stone towards it in terms of nightly rates or amount of data or volume of the universe surveyed in a single image. And NSF like us for that reason as well. So it's a good project to be involved with for figuring out all the things that you're going to need for LSST. So let me talk about ZTF a little bit more. So Samuel Oskin 48-inch telescope was built in 1950. This is the fastest sports car at the time. It had a top speed of about 125 miles an hour, roadworthy car. Here we are now in 2019. This is a Bugatti Chiron, which has a top speed of about 260 miles an hour. So in terms of sports cars, we've doubled the speed we can do at. We're using a 70-year-old telescope. It's been refurbished in terms of the camera and the optics and everything that we've put on top of it. Versus a photographic plate, we're looking at a data collecting rate of about a factor of 1,500 more. So sports cars have doubled. Astronomy has gone by a much larger factor in terms of the amount of information, the amount of data we can cover. So what we have is ZTF is this 47 square degree field of view camera. It's made up of 16 CCDs. It sits in the tube of the telescope. We have an electronics rack there. We have filters there. We have a robotic arm for doing filter exchange. We have this nice table tennis sized table shutter which opens in half a second when it works properly. And we're on sky, you know, as many nights as we can be. Our field of view, just to give you some idea, relative to some other surveys you may know of. So this is the full moon. So we cover, in a single ZTF frame, we cover 260 full moons worth of sky coverage. This is LSST. It's actually smaller than ZTF, but they'll go a factor of 10 deeper. This is Pan-STARRS. This is PTF, which was the previous instrument on the Samuel Oskin telescope, much smaller field of view. So, you know, we increased our field of view by a factor of 7. Dark energy survey, hyper supreme cam. Some of those go deeper, but we're certainly the largest on-sky thing at the moment. This is what we actually look like in practice, and let me see if this will run. So this is, here's the camera, here's the shutter at the end. This is our filter exchanger. So the robot arm sits in. We have a complicated system of latches. Southern California is an earthquake area, you may know. People get rather concerned if you've got something robotic which is changing sheet pieces of glasses above the mirror, and what happens if we have an earthquake as it's going. So we have multiple redundancy in. So we have this cassette here. It changes it. It'll take a new one, puts it back in place. This takes about 3 minutes overall to change filters, but it's all robotic in the night. So we have a scheduler. We'll do a bit of sky. We move to a safe stow position. It'll change the filters, and then we move back onto sky, do another bit, move back, change, and whatever through the night. So we don't need to do a filter wheel. Everything sits within this. The filter wheel was too much of a solution for this. So I think we're the only survey which actually has this sort of robotic arm. Interesting thing about robotic arms is they don't like the cold. They don't work below about 5 Celsius, and you would have thought robotic arms are designed to work in areas where humans cannot. So it has this neoprene sleeve on. You can buy these on Amazon, sleeves to keep your robotic arm nice and warm in the cold. It's, yeah, anyhow. So what have we observed so far? So ZTF is a private public funded survey. We get about 40% of our money from NSF, which means about 40% of our time goes towards sky surveys, public sky surveys. We have a consortium which provides another 40% of the time, and then CalTech has a 20% share. The CalTech time just feeds into the regular CalTech observatories, and so we have faculty and postdocs who apply for that 20% of time for their programs. The partnership defines the various programs they're interested in, and I'll talk about the public time in a minute. We had first light in October 2017. We've been going, we had operations start March 2018, so we're coming up to a year on operations now. We've effectively covered the entire sky now, in some areas up to about 1,500 times. We have some deep drilling fields that we've done. We have a G filter, we have an R filter, we have an I filter internally for partnership. That's observed a lot less because there are specific programs for that. But for general observations, we have lots of data in G and R. One of the things we've been doing is building up a reference map of the sky. This is very important for doing the transient science we're interested in. I'll talk a little bit about that more in a while, but it means that we need about 60 observations of every bit of sky typically to be able to create a nice co-added deep image, which is then our reference point for any observations on the sky for detecting things that are different. The 40% of time for the public time, this is at the NSF-funded stuff, goes into 2 public surveys. So there's a Northern Sky survey. So it's 2 visits per night. We cover the whole northern sky every 3 nights on average. So it's, 24,000 square degree total footprint. We cover about 4,500 square degrees per night on average, something like that. Yeah, nothing to say about that. And then the galactic plane every night in GNR. So that data will all be ostensibly public soon. We do an alert stream. So when we look at a particular area of sky in a science image, we take the reference image and take the difference between the two, and anything that's a 5 sigma detection in that difference image, we send out an alert on. We do this in real time. It's about 20 minutes between the observation taken at Palomar and the alert going out. The data from that we take from this program, those alerts are available to the public in real time. There are systems that you can go online now and get those, and we're sending about several 100,000 of those a night. LSST will increase that by about a factor of 10. And we're averaging roughly good times on the 2 programs. So we are doing what we said we would do. These alerts that we send out, it's a complicated data packet. You get a thumbnail of what the new thing is. You get a thumbnail of what the reference image is. You get the difference. And so in this case, you can see there's a nice supernova probably sitting there. 63 by 63 pixels. We give you a whole load of metadata from the pipeline, parameters that have been measured, the distance to the nearest pan-star source, the distance to the nearest solar system object, stuff like that. We also give you a 30-day rolling cadence light curve of all the previous detections or upper limits to null detections for this particular position on the sky. So the idea is that all the information you need to know about the thing that we think is something that's changed, whether it's moving or whether it's exploding or whether it's just variable, is all in there. And there are now at least 3 systems online. Los Cumbres Observatory have a simple broker service. NOAO have this Antares service, and there's a service at Royal Observatory Edinburgh, Le Serre. You can go there, you can say, well, I don't want several 100,000 a night, I want all the things that look like supernovae or all the things that look like cataclysmic variables, and there's a subscription service as each of those which will allow you to get that feed then from the public data, and then you can do whatever you want with that.
Is this subtracted the difference, or
is the subtraction is a difference image between the 2.
Why do you send it?
Because you want to see what you could do it yourself, but we'll give, if you like, you can do that yourself and do the effort yourself, but we include it because you can just look at it and see, our algorithm is optimized for our telescope system. You may have a better idea of what you want. The data, you would have the reference in science and you could implement your own one there as opposed to what we're doing. But there are lots of people who don't want to do that, and so they're happy with what we believe is optimized for what we're doing. One of the problems we have are crowded fields. This is the Andromeda image. As I say, one of the things we have is we do these nightly observations of the galactic plane. So Catalina never did that because it was too difficult. ZTF decided to do it. And so we do have science questions about how to do things optimally in crowded fields. And Pavlos and I were talking earlier about there may be some sort of computer vision problems there, or you could reframe that as a computer vision thing, so there may be some interesting projects there. the basic line is we already have more data than we know what to do with, and we're going to be producing even more data that we know what to do with. So there's lots of things. All the images from last year will become public on May the 1st through IPAC. And so, yeah. Now, I said that the alerts work through this difference imaging for detecting things that have changed. And that's fine for a lot of things. I mean, that's fine if you're looking for supernovae or stars that, exploding things or moving things. But the sorts of things I'm interested in scientifically vary on much longer timescales and are maybe as significant in their changes, but they may be slower in doing that. And so what it means is that, because this has to be a 5 sigma detection in the subtraction image before it triggers an alert packet to be sent out and say, hey, this has changed. It means that with magnitude, with brightness, there is this, there's this relationship about how big this change has to be before it triggers the alert. So if you're bright, it doesn't need to be so significant. But if you're at the faint limit, let's say 20th magnitude, then you need to have a delta mag of about 0.5 or 0.6 for it to be equivalent to that sort of change. And where this becomes a problem is that these are both AGN, both quasars. So this quasar for 8 years did nothing, and then it did this significant flaring event, but that whole flare took about 3 years. And so this is what, 20.3, and so it puts me up at about here at the significance level. So I would have only caught this at the very tip of this particular activity, only at the very tip. And that's 500 days into that phenomena. So if I wanted to actually understand what was going on with the object as that was ramping up, I wouldn't have follow-up capability until this thing was actually at its brightest. Similarly, this is a thing called a changing look quasar, which I'll talk about a bit more. Again, sort of, it's a very slow trend. Again, sort of 8 to 10 years time. And I would only actually see this relative to what's going before, sort of 2,500 days into the thing, as opposed to 3 days or the same night, which is what I would do if I was doing supernova. So there's a whole class of objects out there which are doing interesting things on much slower timescales that I can't get through differential photometry. So the question is, how can I detect these? Or the problem has been, how can I detect these in other ways? Now, Catalina gives us this 10-year baseline. There are other surveys. I can go to DASH. I can add 50 years or 100 years worth of data. I can get the historic behavior, a lot of these things. But is there then stuff I can do on top of that to say, I expect it to do this? So we have this wonderful taxonomy of variability from Laurent Ayer in Switzerland, and most of these are periodic sources. And most of our variability studies in astronomy to date have been working on periodic sources because they're nice and simple, and you can, Pavlos and I can tell you about lots of period finding algorithms and which are the best ones to use and whatever, but you can detect periodicity and you can say that's a periodic source and I can fold it and I can do interesting things with that. But in terms of the actual population of astronomical sources, this is 5%. Most sources are not periodic. Even in this classification, in fact, there are some. So there's AGN there. Okay, if it's an AGN, we don't care about it, and a lot of people don't care about it. If it's a red giant of some description, they're complicated things. If it's a white dwarf with an accretion disk, that's a complicated thing, so we don't concerned about that. But aperiodic sources as a population are, as I say, the largest one in astronomy and cover a lot of different things. There's a whole load of accretion system-related phenomena which give you aperiodicity. Whether those go from compact stellar systems a white dwarf with an accretion disk to the supermassive black holes that I'm interested in, which is 10 to the 8 much larger. Young stellar objects, planetary disks, planetary systems, or galaxy formation. Red giant stars have these complicated multimodal chromospheric layers which are doing very complicated things. They look sort of semi-periodic sometimes, whatever. You get things like Boagian's star, this very weird star with this cloud of exocomets around it, potentially, or maybe it's an alien megastructure, I don't know. But it behaves in a way that's not easily predictable, reproducible. And then you get stellar processes or stellar associations, all sorts of things. You get objects like this. This is GSR 1915. This is a microquasar. So again, it's some sort of hot, compact stellar source with an accretion disk around it. But this has 15 different identifiable states in it when you do the time series analysis. And some of those are deterministic. They have names like heartbeat. Some of them have been identified as being purely random, and it sort of does these very interesting transitions. This would never be periodic. So the question is, but what I'd like to do is I'd like to understand in the behavior of this class of objects, can I identify when it's behaving in a way that I would not expect? Because then it becomes interesting. I mean, they're interesting in their own right. But when they become really interesting is when they start doing something that's indicative of something unexpected. Because then I can go to a 5 or 10 meter class telescope and get a spectrum of it, or I can go to HST, or I can go to Chandra and get multi-wavelength, more information about it, so I can really understand the processes that are going on there then. And can I characterize these in a way which allows me to understand different physics that may be going on, or different processes which may be dominant through a behavior phase that I'm not necessarily expecting? So quasars, this is the sort of population I work with. First quasar identified with 3C48. First quasar was 3C273, but one of the first identified in 63 was 3C48. There's a paper by Sandage and Matthews from then. One of the things they say is the most striking feature was that the optical radiation varied. So we've known from day one that quasars, AGN, are variable sources in an interesting way. Thing is, 56 years later, we still don't understand what the physical origin of the photometric variability in the optical or the UV is. It's something to do with the accretion disk, we believe, but whether it's explosive phenomena in the accretion disk, or is it microlensing, or it's stellar collisions, or magnetic turbulence, we don't know. We have these nice models of how we believe the structure is created and whatever, but it's something to do with what's going on here in the middle, close to the supermassive black hole, and we can observe it, but we don't have very good behavior patterns. So one thing I've been doing with the Catalina is, because there are lots of these things known. There are about 500,000 spectroscopically confirmed quasars from the Sloan survey. You can add another 1 million high probability photometric candidates to that. So you go to Sky survey, which has got 500 million or 1 billion objects in there, you can quite happily pull out a nice large data set of 1 million time series of what these things look like. And that's what I've done with Catalina. And you've got 10 years worth of baseline, and it's reasonably well sampled. And you can go, okay, well, let's find the stuff that looks odd in there. And you find things like this, where you've got, it sits along, does nothing, then it has a big flare, and then does it. Or maybe they're doing some sort of microlensing. So there's still the unexpected behavior above and beyond what the rank and file does. Or, as I say, you find these changing look things, where in the optical photometry, they have a behavior which is very slow and consistent. You then go to a telescope and you get multi-epoch spectroscopy, and you find that there are emission lines which are turning on or turning off. So there's something going on here with this class of these, or this subset of quasars, where there is something very dynamic happening on year to 10-year timescales in the accretion disk, which is changing something in the accretion disk so that we're actually seeing, emission changes. We think maybe it's some sort of ionization front that's propagating through the disk and changing the structure of the disk, but we don't know. We need more of these. Again, the problem, however, is with all of these that these were found through archival searches. I've gone through 10 years worth of data and said, 5 years ago, this did something interesting. I can show you what it looks like now, but wouldn't it be great if I could find this tonight, and then for the next 3 years, I can get an observation every month or every 3 months and track it as it's going through this slow transition, and figure out what's going on. Have a better insight into the actual physics. Part of the problem is so we don't have a good model really for quasars. I mean, we know what the light curves look like in the time series. We don't know if the types of time series we're seeing are actually genuinely stochastic. Is it really random, or is it just very nonlinear? Is it deterministic in some way? That, okay, we have an accretion disk and it's got gas and it's got turbulence and it's got magnetic fields, but ultimately it's still, there's a simple differential equation, a normal differential equation or set of partial differential equations I can put together to describe that behavior. Or is it some ensemble of unknown processes, which means that there's actually so many degrees of freedom that really the best description for it is a stochastic differential equation. And so that there's this sort of, very, very random type sort of stuff going on. It's a very fundamental question, and I think it's one we really haven't thought about too much for this class of objects. And our data now are beginning to get enough where I think we can get some more insight into it. There's an old theorem, and Jeff Scargill wrote about this in the late 80s, called Walds Theorem, which says that if I have a stationary process, I can actually decompose it into sort of a stochastic component and a deterministic component. And GSR 1915 shows that this is the classic example. I said there were 15 states there, and some of them are deterministic, some of them stochastic. It'd be great if I could do that for quasars generally, and say, well, okay, there's this pattern of, or there are these types of behaviors which I can associate with gas dynamics. These are the types of behaviors I can associate with things with, relativistic magnetic fields or whatever. So AGN variability for a long time was described really simply. In fact, what people did was they'd say, well, DPOS was taken, let's say, in the 90s, Sloan was taken in the mid-2000s. I'm just going to find all the things that look as though they've changed by a magnitude between those two data points. That's going to give me my class of objects. I'm going to look, this is what they look like in color space, and therefore they're interesting. More data points came through as we get more time series. Then you start moving into, well, I can do a reduced chi-squared and sort of say, well, those are more variable than those. I can do something with a structure function, maybe. Very popular historically as a descriptor of variability, not necessarily the best for getting information out. Lots of different estimators used in the literature, all of which disagree with each other. 2009, Brandon Kelly came along and said, well, look, there's this really simple stochastic model, statistical model, first order continuous autoregressive process, also known as a damped random walk, also known as an Ornstein-Uhlenbeck process. It's been known from the 30s. A solution to a very simple differential equation, stochastic differential equation. It gives seemingly good fits to quasar variability. It's characterized by two parameters, one of which is the variability amplitude sigma, one is a characteristic time scale, a sort of relaxation time, and it's great. And what I can do is I can fit a whole load of quasar time series with it. I can say the amplitude and I can define a 2D parameter space. Quasars lie here, stars lie down here. I can use it to identify quasars on the basis of a variability in photometric surveys. All great. Very popular, still the most popular model. People have done some more studies of it using Kepler data, using different ways of looking at it. Sort of say, well, okay, not actually quasars, not all quasars are well described by this. And then there's been some more work which sort of says, well, actually, this is not actually a really good descriptor at all. People have said, you know, with these parameters that they're correlated with physical parameters like the luminosity or the Eddington ratio, how much the accretion rate onto the disk or the supermassive black hole mass. Kozlowski, in the last couple of years, has shown that those correlations are false. There's a problem when you try and estimate those parameters from a time series. Your characteristic time scale, tau, you actually need 10 times the length of that in terms of your data coverage. So if your characteristic time scale is 1 year, and you're looking at a quasar at a redshift of 1, so that means it's going to be 2 years worth of data. You need 20 years worth of data then to estimate statistically reliably that the characteristic time scale is 1 year. If it's at redshift 2, that means you need 30 years of data. If it's at redshift 3, you need 50 years worth of data. So lots of people have been using Stripe 82, which has maybe 3-4 years worth of data, and estimating this and underestimating, and it gives you false correlations and all sorts of problems. So big problem with that as a model, but can we do better? So damped random walk is, as I said, a CAR1. Now there's this whole superfamily of processes. So a CAR1 is a Karma 1, which is a Karima 10, which is a Karfima 10. These add more additional terms. People like to model stock market with this sort of thing, and these are all more sophisticated, more generalized stochastic models of variability of some description. But they all suffer from the same problem. In fact, they add more parameters that you underfit instead of making the problem simpler. So one of the things we've been looking on, one of the things I've been looking at is different ways of thinking of these problems. There are these things called Gaussian processes, which are a really nice way of non-parametric, Bayesian, give you really good for interpolation, good for regression. And a Gaussian process is essentially, if it's a zero mean process, so you can just take the mean away from your time series if you believe it's stationary. It's completely defined by a covariance function, which is an equivalent kernel function. So I can make an assumption about the process that's driving my time series, my process, encode that as a kernel function, fit it, and then I can get meaningful information from that. There is a class of processes. So there's this Karfima, this very sophisticated one. There's a thing called fractional Brownian motion, which comes out of more nonlinear physics. And you can look at it and think of it in terms of, it has, relation to Hurst exponent and to measures of chaos, the things like the Lyapunov exponent and whatever. That maybe give you a better handle onto some of the nonlinearity of what's going on. And so we've been playing around, I've been playing around with this kernel instead. It has a very simple functional form, and I can fit it to a quasar time series. This is a damped random walk fit to my quasar time series. This is a fit from this Cauchy kernel, both with both encoded as a Gaussian process, and I get a much, well, the fit is equivalent to what's been done so far in the literature. For a lot of objects, I get a much better fit with this particular kernel function. And one of the things we're looking at is, because this kernel function is motivated out of nonlinear physics as opposed to something which is stochastic and may not actually be reliably applicable to the type of object that I'm actually seeing or the type of behavior. I mean, I know, because I'm looking at a physical system, that there has to be physics behind it. The stock market has no physics behind it. It's purely, and it may be entirely stochastic, and so that's perfectly described by one of these stochastic processes. But gas going around a supermassive black hole falling in obeys the laws of physics. And so there's a better motivation for having something physically describing that into that. So that's one of the things we're thinking about. In terms of predictability, Gaussian processes aren't the best, but there is stuff that you can do with this kernel representation and local measures of chaos so that you can make short-term predictions which are maybe as good as some of the other things that you can do. And we're sort of playing around with that a bit. But another way that we can try to do the modeling is through neural networks, and particularly good, deep neural networks. They're trendy, good for funding proposals. I'm going to write a proposal to NSF. You say, I'm going to use a deep neural network. They go, oh, they must know what they're doing. Convolutional neural networks, people are probably very familiar with. Current game changer for images. You can use these for time series. And there's been some work done. What you need to do is you need to convert your time series into an image representation. And then you can train your CNN on that set of images. Ashish Maharbal, one of my colleagues at CalTech, has done this with variable star time series. So what you do is, here's your time series. You measure the change in magnitude and the change in with the change in time. So the change in magnitude is dm between 20 points. The change in time is dt. Those map into this dm dt space. There's some optimal gridding you use for this, and then it converts it into a 64 by 64 JPEG or whatever, and that's the thing you feed through the CNN then. And it turns out that with a particular optimal gridding, different types of variable stars have slightly different dm/dt images, and then you can do classification on that. Fine for things that have that well-defined behavior, not so great for things that are aperiodic, which would just smear across. Yes?
Why are you turning stuff into 2D? There are deep learning methods that are 1D.
I agree. The issue here is that they want to use CNNs, and a lot of the CNN architectures have been, if they're taking an off-the-shelf CNN, it's designed for image, and so that's there are a number of people who've done this. I agree it's not necessarily...
The DMDT is a two-dimensional feature. Abstraction.
Yeah. Yeah.
What's the advantage of using the images rather than... What's the advantage of doing the images, apart from just wanting to use CNNs?
CNNs are... I'm not certain there is an advantage. It's just what people have done. RNNs are a little more, I'm coming on to RNNs, but the thing is that the technology was already there. There are off-the-shelf libraries people can apply to it. They're cheaper to train. And, ImageNet and Google and whatever, great store, and you can go and find the Jupyter notebook which tells you how to apply this to tell the difference between cats and dogs. And you can convert your time series into images and apply the same architecture to it, and you get a result. That's as good as more traditional machine learning random forest type things. So I think it's just ease of application more than anything. As you'll know, there are neural network architectures, however, which have memory, so you get links between the things, and these are much better suited for sequences and time series. So, maybe what you can do is if you want to use this DMDT still approach, instead of having the whole time series, you have some sort of sliding window, which then gives you a succession of images. You can feed that into some sort of net and do something like that. The ones we've been playing around with AGN are RNNs, or specifically an RNN autoencoder, because we want to do several things. So we've been playing around with various architectures. This is just the one we've got working at the moment. So one of the challenges is that we have horribly irregularly sampled time series. So therefore, we have to So what we could do is we could fit all our time series with, Gaussian processes and then regularize it in some fashion, but then we've got to make an assumption about what our kernel is going to be, and that introduces problems again. So we're looking at a couple of different ways of encoding the irregular time series. One is that we actually use it as a feature. So instead of just putting the observed magnitude and the magnitude error and getting the network to train on that, we also include the delta t between successive steps. We put it in there as well. Another one, because we're more interested in prediction as well, this predictive modeling, is that not only do we put the time step to the next object, we also then put in the velocity and the acceleration so that we can maybe get a slightly smoother fit, because again, we've got this sort of slightly jumpy thing going around. So this is what we've been playing around with for about the last 9 months or so. This is myself and a Japanese student at Tokyo Tech, Taro Tachibana, who's just writing up. So what we've been doing is we took, a training set of 40,000, 30,000 quasars, nicely well sampled from Catalina within nice magnitude ranges, got rid of all the ones that, had noisy stuff or whatever. And we train over that with these networks. And then we compare it to damped random walk, because that's the comparison model. So what we find is a number of interesting things. We find that actually with the autoencoder, we get a better fit to the AGN time series than when we do with the damped random walk. So that's nice. It's encouraging, because it means that there's actually something in the time series that the autoencoder is picking up on that the damped random walk model doesn't. And that's probably suggestive of nonlinear physics, as opposed to maybe stochastic stuff going on. What's even more interesting is, so we can generate a damped random walk model because we know the parameters and we know how to do it, and we can then fit it with one of our RNNs, and we can fit it with the standard way of recovering the damped random walk parameters. And you find that the RNN actually does a better job at fitting the simulated data than the standard ways of, have I got those the wrong way around? Yeah, so that's the RNN. That's the standard way of fitting. The standard way of fitting underestimates. So you do MCMC or you do something like that. It underestimates because of this 10 times baseline problem that you have. Using the RNN, you don't seem to suffer from that 10 times baseline problem. There's information, or it's more, whatever. And so what you find is that the autoencoder does as well as the true parameters, whereas the recovered parameters give you a much larger reduced chi-squared. So even if we simulate damped random walk, we still do better in recovering it, modeling it, than the damped random walk model that you would do if you're trying to fit in the first place. So these RNNs seem to do really well in modeling. Because we're looking at an autoencoder, we can go to the latent feature space and say, okay, well, so we used 16 features. And we can sort of say, well, what is it that you're picking up in these? I mean, the quasar time series, they don't line up. You can't register them. They've just got various features. What is it that is picking up? And you can sort of say, well, here's, we can take the 16 autoencoder and features and do a dimensional reduction down to 2 dimensions or something, t-SNE or something, and say, okay, what are we seeing in different areas? And you can sort of see there's sort of different things that it's coming up with. There's nothing that sticks out and you go, oh, that's a really obvious thing that we can tie into something physically. It's probably smeared across. And in fact, when we look at, if we take all 16 features and reduce it down to a single feature, we find that it correlates with in this case, Eddington Ratio, as well as any of the other features that people have reported extracting from time series and correlate with physical stuff. So there is physical information in the time series that the RNN, the autoencoder, is picking up on that we can recover. Now, I can't tell you what it is, but I can tell you the information is there and that it correlates in terms of feature space correlating with physical parameters. Part of what we're trying to do is to understand what actually is it picking up on. But there are these correlations there with the black hole mass, which you would expect. So that's all modeling stuff. That's all, in some ways, discriminative. But there's also this thing, as I was saying back when, that RNNs, they're modeling the AGN better than the random walk model. They're providing me a model, but they also have a predictive component. So can I use them then to say, well, okay, here is 10 years worth of time series. I'm going to train on that, and I'm going to make a prediction for what the observation will be that I will make tonight, what the photometric magnitude should be. And so we've just begun to play around with this. So it's very preliminary. So this is the trained. This is where I use delta t, y, and y error. This is where I use delta t and the derivatives. So with the derivatives, I actually get a slightly nicer fit to, in this case, and there are other examples where I get a slightly cleaner fit to the actual time series that's going on. And then in terms of predictions, so we're making predictions, well, Catalina ended May 2016, ZTF started March 2018, so it's about 700 days, and that we're predicting out to. And it's reasonable agreement for a lot of the things. So what we're interested in, it seems to be working. What we want to find is actually, can I find the things where the agreement is not good? Because then those are the objects where the behavior is different from what I would have predicted from my model to what I would expect to see. And we have identified some of those. We're now going to the telescope to do the spectroscopic follow-up to see if it actually is doing something more interesting than we thought it might be doing, or whether our modeling is all wrong. And then going beyond this, I mean, a lot of this, these are pretty much off-the-shelf RNN autoencoder type things. There are deeper processes that we're maybe interested in sort of playing around with more. Gaussian processes, there are deep versions of those where you get more layers. There's the sort of overlap between Gaussian processes and neural nets where there's that sort of thing going on. Deep kernel learning. We've been talking with folks at Amazon about deep autoregressive processes going back to that random walk thing, but there are deep versions which may be less stochastic and maybe have better ideas and that sort of thing, which people have been applying. So, in summary, the sort of traditional time series that people have done using very discriminative models. And you put those into random forest and hope that helps your classifying, but doesn't do anything for prediction. With these sky surveys that we have now, we have enough data to do individual modeling of objects. So we can do a prediction of what their behavior should be when we next look, and we can go and we can validate it. So I think the thing is that we're moving into an era now where the volume of the data is such, and the computational techniques, or the statistical techniques we have as well, are such that we can do more intelligent monitoring of these things than just saying, well, has it actually changed by 5 sigma? And I can't tell you what that change is. I can actually model this and say, look, this is changing in a more subtle way than I would expect it to be. And then we get a better idea of what maybe is going on underneath. And in the case of these aperiodic sources, maybe we'll be able to actually understand, what is stochastic and what is deterministic in terms of the phenomena that we're seeing overall, and then that gives us a better handle on what actually the physics behind this variability we're seeing in these classes of objects. So I'll leave it there.
We have time for questions.
Yeah.
How do you label what is normal, what is abnormal? You might label different things as the same as normal, or you might leave out some abnormal into the normal.
Yeah. So there's that great line, isn't it? Past performance does not guarantee future returns. The assumption, our assumption of normality is what it's done over the last 10 years. So if we model the last 10 years worth of behavior and we make a prediction for what it's going to be, and the observation falls within that prediction, we assume it's behaving as it has been doing for the last 10 years. If we make a prediction of where it should be and we make an observation and the observation is very different, we can put error bars, we can put a 1 sigma estimate on what the error bars should be on. If it's significantly different, then we call that abnormal behavior. So it's, if it's doing something unexpected in the sense that the model it's not behaving as the trained model would suggest it should be, that's what we then call unexpected. But what we need to do now is, and that's when, so those flags up the interesting objects that warrant further study. You do the further study of it and you go, oh, actually it's not unexpected behavior, it's blah. We need to retrain the model by feeding some more stuff into that to cover that sort of thing. But it's going to be an iterative process essentially to understand what the, I mean, we're assuming that 10 years worth of data for 40,000 quasars should give us enough of a representative sample of what the expected behavior across the population is. But I'm happy to say maybe not. I mean, maybe you need 100 years worth of data to get the full sampling. But yeah.
Have you been able to learn anything from meteorological modeling, which has the
Yeah. So we have. So I didn't touch on it so much, and I just sort of glossed over it. The stuff with the Gaussian processes, where we're using the nonlinear kernel. There are a couple of papers from climate modeling in the last couple of years where they've been doing these very similar approaches where they use localized chaos measures, and then you can put that into a Gaussian distribution and then look at the range of predictions to get some idea of what the next step might be when you take a measurement, and similarly. And so we're trying to play around with some of those as well. But yeah. Again, I don't know, I don't know whether quasars behave the same way as the climate. I can tell you quasars don't behave the same way as the stock market, because we tried fitting stock market models to quasars and it doesn't work. The stock market is actually far more volatile than quasars are, at least on the long term. So there are, particular types of models that just don't work at all for quasars. So that's, I can tell you what doesn't work, I can't tell you what does work, but.
The predictions you had, is there a reason that there was a kind of like derivative discontinuity?
Yeah. So.
Because you were in a sort of like high data area just before. So I was like.
Yeah, well, so I think there are a number of things going on here, and there are things to be addressed. One of the problems with this model is because it's just delta t and y. The time sampling you use then for when you're making prediction gives you some slight variance in, if you go for irregular versus irregular, that seems to introduce some component instability. This model gives a much better, but this is not then feeding in, this is not feeding stuff in as an auxiliary component to the network. So what I need to do is I need to combine the two, and I think that might solve some of the problem. That this discontinuity here is actually some effect that I'm maybe not have enough derivative information as I'm going forward. And I need to play around with that sort of thing.
If you have taken half of this data here
Yep.
and forecast forward, How does it look like?
So when we do the training on this set, for example, what we do is we have 4,000 days time series. We train on the first 3,000 days, and then we test on the final 1,000 days.
Yeah, I understand, but
Yeah.
when you test, you give the xt minus 1 as an input,
Yeah.
right? But if you haven't given that, what would be the equivalent prediction if you just hidden the whole thing, right?
If I just take that and see where it goes,
Yeah.
it looks reasonable. Yeah. In some cases, on other cases, it's not. And part of the...
Do you have, did you qualify the forecast?
Not yet, no. This is, we are here now, and...
Well, but you could test them all if
Yeah,
I just
yeah.
hit the data and try that. Okay.
Now, what part of my suspicion is that if you do that, you may not have, on shorter timescales, enough information to... What I don't know is how much information, how long a baseline you need to be able to forecast. And some of it I know is going to be related to the characteristic timescales of the processes that are involved. And I know that those are, you know, months to years. And so you need at least a long enough baseline to have a reasonable sampling of that in your model to capture that information to go forward. And so it may be that with only 5 years worth of data, I don't actually have enough information for some sort of objects going forward.
Yes. Do you think you can use this to eliminate certain models of the physical phenomena that might actually be going on?
That's the hope. Yeah, no, I mean, yeah, no, I mean, that's the hope, or at least to, I think it's more, I think maybe not such a high goal, would at least be able to identify certain subclasses of object which seem to be behaving characteristically in the same way, and then to correlate that with spectroscopic information or multi-wavelength information to verify that and sort of say, oh, you know, there's a class of objects here, there's a class of quasars here where obviously there's some sort of radio jet going on and we're not seeing the radio jet, but that's having some effect. Or, you know, there's this class of objects where there's a hot X-ray corona, or they lack a hot X-ray corona, or there's some dust or something. So I think, yes, I think there's a more detailed quantification possible of the optical photometry and the optical time series through a better characterization through models which actually provide a closer fit. And so,
Models and actually try
yeah, yeah,
the
yeah.
comparison.
So I think so, yeah.
All right. Thank you, Matthew.
Okay.